Hi everyone. Very happy to be here today to talk about determining material properties for novel materials, focusing on a case study in bamboo. So we have a climate emergency, of course, and because of that we need to look into alternative materials. We can't just use the higher carbon materials that we frequently use, so there's a big interest to use lower carbon materials, especially timber, and there's a growing interest to use other low carbon materials such as bamboo and soil and others. Now, when we think about lower carbon materials and bio-based materials, if you compare them to modern engineered materials such as steel, reinforced concrete, steel for example because it's man-made, we can be very confident regarding the design strengths that we have. It comes off a production line and the standard deviation of those strengths is very, very low. Hence, we have very low factors of safety on the material side. Reinforced concrete, it's man-made, but slightly larger standard deviation because the spread is naturally larger, so the factor of safety is a little bit higher. When you compare that with timber or bamboo, the factor of safety and the standard deviation is even higher because these are bio-based materials and they vary quite a lot, and it's naturally there's this high variation. So this is something we have to think about when we want to use them for construction. So how does one determine material properties for structural design for novel material? I'm going to focus on bamboo, but these principles will apply for other materials. So let's say you're working on a project and someone says, let's use bamboo or let's use some other bio-based material for construction. What do? First thing I'd always recommend is a simple literature review to think about, does reliable test data exist for this material already? Is the format clear? Is there any data on what variables affect the strength? So the first question is, does reliable test data exist for this material already? That's really important. There's a lot of very good publications out there, and one can look at that. One can do a simple Google search and then look at more academic papers to see what test data exists. But reliable is very, very important. We need to look at the source. Is that a reliable source? Is it a scientific journal? What level is that journal? The quality of journals vary significantly. How much testing was conducted? Is the format clear? When I say format, has the data presented as just this is data? Or does it say these are average tests? This is the results. These are the average strength results from a set of data. Well, are they characteristic? Are they ultimate? Are they design? And that's very important because I've come across a lot of data that's published that looks very reliable. It doesn't even say what that data is. It doesn't say if it's ultimate, average, or characteristic, and that's incredibly important. And then we also need to know is there any data on what variables affect the strength. Bio-based materials, there's lots of variables that may affect the strength of, say, timber or bamboo, for example, species, but also where that material's from geographically, and maybe even the part of the culm or the tree, its exposure to wind, its age, and so forth. So 2 examples here. This is a publication we did for the Structural Engineer a few years ago, and we intentionally published reliable data, but we've specifically said the format. We've said this is a characteristic strength for dry, mature bamboo that's been graded, assuming a 10-minute load test at 12% moisture content. I mention this because I've actually seen very few publications that will be so clear in terms of what that data is. And that's really, really important. If you don't see that, it's not necessarily that reliable. Just for fun, I threw this into ChatGPT yesterday. And what do I get? Well, I got some sensible results and some results which were, let's say, not correct. So I asked what are typical design values for bamboo. It spat out decent compressive strength, shear and modulus of elasticity, and then tension and bending strengths which were completely incorrect. So again, be very careful of ChatGPT and many sources. I know where this has come from, but it's come from incorrect data. So just be cautious about that. Next, we need to define the source. And again, I'm focusing on bamboo, but the same will apply for other materials, not just bio-based materials. So again, we can use existing literature combined with engineering and judgment. We need to define an appropriate source or supply. And that should be ideally as narrow as possible. So firstly, geographically. Species as well. There's over 1,000 different species of bamboo. What species are we going to use? Geographically, are we going to look at this species globally, or are we going to take it just from, say, Colombia? And are we going to take it from one part of Colombia? Bamboo, for example, strengths in different species. For different species, the strengths will, of course, vary, but equally geographically for the same species, the strength will vary, just like timber. And even within one country, the strengths will vary depending on the soil condition, depending on the exposure to wind and so forth, altitude, heat. So there's a lot of variables. We also need to define a possible grade. So again, the age of the bamboo, its condition, we want it to be in good condition, of course, the diameter, height along the culm, and so forth. And again, the same applies for other materials. So we're starting to create a possible grading regime for the future. Next, we need to specify appropriate preliminary testing. So we can think about what material properties do we need to know. Is this material similar to other materials? Can existing test standards be used? And if not, can they be adapted? So for bamboo, for example, we adapted timber standards. It's very similar. We had to make some adjustments, but we had a good starting point at least. And again, for most materials out there, for most novel materials, you can simply learn from what's already been published and use it directly or adapt it using engineering judgment. Testing should be designed to isolate each material property separately. For example, shear versus flexure. So if we have a beam, we want the test of the beam to be long enough so we force a flexural failure rather than a shear failure. And that's very important. So we're very clear on what the testing is actually trying to get. Next, while we conduct preliminary testing, we should test a healthy sample size for each material property sought. If we're in preliminary testing, and again, the more tests, the better, but as a bare minimum, we normally recommend 5, and anything under 15 gets severely penalized when you look at the statistics. In terms of interpreting, you can use Eurocode 0 Annex D. It gives some very useful methodology for that. If you do follow that method, you'll get to a point where you've determined the characteristic value from a set of data, but what about the factor of safety? So for new materials, there is no clear, simple way to determine a factor of safety. You've got to use a very complex statistical method to determine that. But again, EC0 gives you a method for directly determining an ultimate limit state value from a set of test data, bypassing the factor of safety, which is quite handy. Next, we need to review that data, review it against literature, source, and testing. Was the testing successful? Could anything have gone wrong? Testing, especially the first set of testing, there will often be mistakes or things we've learned. Maybe the testing wasn't quite right, so maybe we need to update it. Maybe that data, therefore, wasn't that reliable. We should compare that against the literature. If they're quite different, that's a red flag. Maybe the literature isn't correct, or maybe the testing wasn't quite correct. We can look back at the source. Was the source sensible? Does it need to be narrowed, widened, or changed? Now we have the preliminary data. We can review the design. Again, we're at concept scheme stage, maybe. At this point, we can think about, are the strengths adequate for the design purposes? If we're designing something, let's say a bridge out of bamboo, where the loads are quite high, well, we need to be very confident with the strengths. Let's say we're designing an affordable, low-cost house, then maybe the demands on the elements are a bit lower. We can be we can have a higher factor of safety, so we're a little bit less concerned about achieving a very good strength because we can get away with a lower strength. So now we've done that, now we have to repeat the cycle to get basically more reliable results. So we redefine the source and grade. We've learned a lot from that process. We go back, we need to change that source, change the grade slightly. We should update the testing methodology as appropriate. There'll almost certainly be some changes. Do any other failure modes need to be tested? Maybe we've learned that some failure modes are no longer necessary. Again, testing is quite expensive. The more testing that isn't necessary, the better. We should invest those limited monies instead to the testing that we really need. At that point, we conduct testing for detailed structural design. At that point, we need more data. So we'd normally recommend a minimum of 15 samples, ideally 30. If you look at Eurocode 0, you can see penalizations start typically around below 30, and below 15, the penalization is much higher. At that point, we review data and review the design and repeat that cycle as necessary. So that gives you a broad idea about how one can go about looking at any sort of novel material, and it applies for bamboo, but it also applies for others. And a similar approach can be used for connections, assemblies, fire, and durability. If we look at connections, this is a composite bamboo shear wall system that we tested at Imperial College in London. This testing, as you can see, very expensive. What I described before was more about material properties of let's say, a single bamboo culm. And again, the same can be used for any other material. This is an assembly. This is much more expensive by an order of magnitude, if not more. So that's more challenging to do. We'll only be able to do a few tests. The penalisation applies equally to something like that. So that can be a bit of an issue, but it means that we need to be much more careful about the testing that we do. We need to think even more about exactly what testing do we need. But equally, on an assembly, we shouldn't just necessarily test the entire system. It's possible that we can determine some failure modes from first principles using engineering judgment or test them separately. So let's say we're testing a new shear wall. Do we actually have to test for flexure as part of this test? I don't think we do. We can separate that out and say, well, actually, in flexure, there's a stud there, there's a bamboo stud. We can just do a simple compression buckling check of that of that bamboo stud separately. We don't have to test it in the lab as an assembly. Same for the trailing stud. One can do the same for tension. So again, you can remove certain failure modes to force a failure mode which we really need to test. In this case, this was shear. So we tied the panel down, we forced a pure shear failure mode, and that's covered in some of the testings for shear wall, and that way we're being very efficient with the testing that we get. Fire tests are actually very expensive. They're not penalised in the same way. The approach to them is very different, and for those you typically need a fire specialist. But because they're quite expensive, you need to do a lot more thinking about them before. And there's also durability tests, and again, those are approached in a slightly different way, but again, they're quite expensive. And for connections, again, it's generally a similar approach. You'll get penalised in the same way, but for a connection, you can test the entire connection if you don't know about the strengths of the incoming elements. Or again, you can take the connection apart and maybe test the individual elements and isolate certain failure modes to try and simplify the testing and get as much data as you can and really focus on those failure modes that you're not sure about. And that's it. Thank you very much.